Hello everyone, my name is Yang Kaixiang, and I am a third-year PhD student at the School of Life Science and Technology, Huazhong University of Science and Technology. My advisors are Professor Li Qiang and Wang Zhiwei. Today, I am honored to present my work titled CoStoDet-DDPM, Collaborative Training of Stochastic and Deterministic Models Improves Surgical Workflow Anticipation and Recognition. First, I will introduce the background of our work. Surgical workflow analysis is the computational analysis of surgical videos, aiming to model phases, activities, and tool usage. It plays a vital role in improving intraoperative coordination and supporting surgical decision-making. Anticipation and recognition are two of the most critical tasks. Anticipation is to forecast the usage of surgical tools several minutes ahead. This capabilities allows the operating team to prepare in advance and ensure smoother surgical procedures. And recognition focuses on identifying the current surgical phase in real time, which is critical for situational awareness in the operating room. However, there are difficulties and challenges during these two tasks. Due to long-tail variations across patients, such as rare cases in tool types, usage frequencies, and timings, accurate anticipation remains a challenging problem. As for recognition, patient-specific long-tail variations in phase duration and order introduce difficulties for robust and generalizable recognition. Nowadays, different policy in robotic planning has demonstrated that the ability to handle diverse scenarios and remain robust under human perturbations. Such performance inevitably raises the question of whether applying such a stochastic model could benefit SWA. But directly applying different policy to surgical tasks faces two critical limitations. Uncontrollable process. The generated process is uncontrollable, while surgery requires reliable outcomes, controllable and clinically interpretable process, and slow inference speed. The approach suffers from slow inference speed, making it impractical for real-time surgical assistance where timely guidance is essential. Hence, the diffusion policy cannot be directly used in SWA. Then I will introduce our proposed method in detail. We propose a novel approach, CoStoDet-DDPM, which for the first time introduced DDPM into surgical workflow analysis to address long-tail challenges. For our designed co-training mechanism, we established a short long-term collaboration between the deterministic task branch and the stochastic DDPM branch. The task branch focuses on regular instantaneous mapping, while the DDPM branch models a longer temporal window to enhance temporal coherence. For the deterministic models, we directly employed two recent data methods, BM pitfalls and DSAT, and used the features highlighted by the red circles in the figure as the conditions for the stochastic model. Among them, DSAT is a dot branch method. For the stochastic model, we first expanded the temporal receptive field to inject richer temporal information into the stochastic branch. Secondly, since our framework is trained in a collaborative manner, the output of the deterministic model is not affected by the stochastic model during inference. Therefore, the DDPM branch can be removed directly at inference time, enabling real-time SWA. Next, I will show our experiments. We conducted all experiments on 2 surgical video datasets, which include 2 types of minimally invasive surgeries. The dataset splits are shown in the table. The evaluation metrics used in our experiments include 2 types. For anticipation, we use 3 variants of MAE. For recognition, we used 4 metrics. The comparison results with other SOTAS methods for anticipation tasks are shown in the table. The results show a significant improvement, particularly at horizontal equals 5 minutes. The comparison results with other SOTA methods across the 2 datasets are shown in the table. For recognition, as seen from the results, our methods achieve relatively improvements of 1 and 1.5% in J-card index. And here are the visualization results. The upper for anticipation task, the bottom is recognition on clock 80. It is evident that our method, compared to the previous methods, produces smoother, accurate true anticipation in near-use regions, as shown in pink, and accurate face recognition in uncertain regions. Finally, I'd like to conclude our work in 3 points. We propose a novel, top-range, collaborative training framework that explores the simultaneous training of stochastic and deterministic models. And then we introduce a new functionality of DDPM, that is feature enhancement, and apply DDPM for the first time in surgical workflow analysis. And then our method achieves SOTA results in both anticipation and recognition tasks. And thank you for your attention.